Hi, I'm Scott Vaughn. In this video, we will look at a mathematical model of a pandemic. We'll derive formulas for the model and implement that in Excel. We will then compare the results with the common SIR model for a pandemic. I'm making this video because it combines together math topics I teach in discrete math, finite math, linear algebra, and differential equations. There are lots of videos already made on the SIR model and lots of videos that use a discrete model and some that use Excel. But I hope to add something by combining these, putting my own spin on the explanations, and in a way that I can use this with several of the classes that I teach. This video doesn't require an understanding of calculus or advanced math. It really just relies just on a little bit of probability, but otherwise it's arithmetic. This video is a follow-up to a video I made about a year ago on modeling a pandemic with Markov matrices, and I would like to include some comparison here with that previous model. However, a complete analysis of the differences would be an entire video in itself. I want to say thank you to Professor Jacob Glower for his video on Markov matrices and modeling a pandemic, and his suggestions on implementing this in Excel. I will link to his video in the description. Again, a full comparison really would be a whole nother video in and of itself. So I'll just make some quick comparisons with Markov matrices at the end of this video. So we're building a discrete model for a pandemic, and the word discrete here refers to the individual, distinct, different time steps, which would be different than if you did this with calculus. With calculus, it would be continuous functions, and some of the basic assumptions that are in this model are that everyone in the population is encountering everyone else at random. We're going to assume that people with the infection are not acting differently than anybody else. They're just going about moving through the population, interacting with people at random. We're not going to include a vaccine in the model. There's no assumption of any quarantine happening. There aren't any reinfections, so once somebody has the infection, they're either going to be cured or die from the infection. And then we're, again, assuming these incremental and discrete time steps. And some of the variables that I'll work with are represented here. We've got the H sub n is the number of susceptible or healthy people at time n. I sub n, that will represent the number of infected people at time n. C sub n is the number that are cured. D sub n for the number that have died at time n. N will be time 0, time 1, 2, 3, equal steps of time. N equal 1, N equal 2, N equal 3, so on. There'll be a constant cure rate that we'll use that will be this lowercase c. There'll be a constant death rate that's some fraction of the number of people that are infected, how many are dying from the infection. Capital P will be the total population, some initial value that we start with that represents everybody, all the healthy, susceptible, and the infected, the number that have been cured, and total number that have died will represent the total initial population. That total initial population is a fixed number to start. There'll be this lowercase p, that's the probability of an infection given an encounter between somebody that's healthy and somebody that's infected. And then we'll use this capital N as the average number of contacts per person. To calculate how many new infections we'll have in the total number of infections that occur in the model, we'll look at it's the sum of the number of previous infections plus any new infections minus the number of people that have been cured and minus the number of people that have died. So just calculating the number of new infections, what we'll do is we'll make that proportional to the number of people that have an infection and the number of people that don't. So the way I'll calculate that number of new infections will be based on, first of all, the number of people that are currently infected. I'll multiply that by the number of encounters that they would have on average if they're just moving randomly through the population. Then I'll multiply that with the probability of encountering a healthy or susceptible person, and then multiply that by the probability of transmission of the disease if an encounter between a healthy and infected person occurs. And so expressing that kind of calculation in terms of the variables I've defined it would look like this. This is the number of people that are infected at time n. I multiply that by the number of contacts that they could have, and then I multiply that by the probability that they would encounter a person that is healthy or susceptible to the disease. I'm calculating that by looking at the total number of people that are healthy and susceptible divided by the total amount of the population that's alive, that's moving about still in the population. That is the total number of people that are healthy plus the total number of people that are infected plus the total number of people that have cured, just removing the people that have died from the population. And then I'm multiplying that probability by the probability that if there's an encounter between somebody that's infected and susceptible, this P is the probability of the transmission. As just an example of that kind of calculation, imagine that you had 10 people currently in the population that had the infection, and suppose that each of those 10 people would encounter 3 people on average each day, let's say. And suppose that there were 50 people in the population that were susceptible. So 50 people, and then you would divide by the number of people that were susceptible and the number of people that were currently infected. And let's say, just as an example, suppose there were 40 people already cured in the population, so that I had a total population of 50 plus 10 plus 40 more. That's 100 people, but half of them were susceptible, so that's a 50% chance of encountering somebody who's susceptible. And then you multiply that by, let's say, just as an example, 20% chance, if there was an encounter between somebody who's infected and susceptible, a 20% chance of transmission of the disease. So we'd multiply all those together. We'd have 10 people that are currently infected times 3 encounters on average. That's 30 encounters, but let's say only half of them are with people that are susceptible. So that cuts it down to 15 encounters with people that are susceptible, but only, let's say, 20% of those encounters of those 15 encounters between healthy and susceptible, only 20% of them involve the actual transmission of the disease. So we end up with 3 new infections in that particular example calculation. So a quick way to say that might be just there are 10 people that are infected times 3 interactions is 30 interactions, but say only half of those are with people that are susceptible, and only 20% of those actually lead to transmission of the disease. So you end up with 3 new infections in that particular example. So what I've just calculated there is the number of new infections, and that would be added to the number of previous infections. And then we would subtract the number of people that have been cured, and we subtract the number of people that have died. And I'll just make the comment one more time that it's an assumption in this model that once somebody is cured, they wouldn't be reinfected. They can't be reinfected. That's a simplifying assumption that we'll use in this simple model. Now, as I go forward, I'm going to change the order of the way I write those factors, and I'll write it this way. It'll be convenient for what I want to say next, but I've just moved this number of current infections to the factor here at the end. I put this factor, the probability of a transmission of the disease when there's an encounter between a susceptible and infected person. I put that first and put n right here in the front, and I just took out these multiply signs. So I just wrote it this way. That's the way that I'll write it most of the time as I go forward. And so that's the calculation that I just talked through, the way in which I calculate the number of infections at the next time step. So the little n represents a number counting time. So when little n is 1, that's day 1. Then day 2 would be little n equal to 2, and so forth. And so this would represent the number of people at time n that are currently infected. This here is calculating the new number of infections as we had just looked at, and then I will subtract some fraction of the population based on some constant value little c that represents this cure rate. So some fraction of the current population that's infected will be cured, and so that will move into the category of being cured, and some fraction of the people that are currently infected die from the disease, and so they will be subtracted when you calculate the next number of infected people in the population. You're minusing the number of people that are cured, and you're minusing the number of people that have died. And part of the reason why I actually rearrange the order of writing it is to look at the fact that I have an I sub n in every one of these terms. And so it's really measuring the number of people that are infected. They're all like terms. Well, and then the other calculations here are much more straightforward. This is the number of people that are cured at time n plus 1. It's just based on the number of people that are currently cured plus those people that have become cured that we just removed from the infected population. What's being subtracted here is just being added here, and the number of people that have died at time n plus 1 is just based on how many people have already died plus some fraction of the number of people that are infected in the previous time step. The number that have died and that are counted in the next time step is how many had already died plus some fraction of the number of people that were infected. Another thing that I will be keeping track of course, is the number of healthy and susceptible people, which I call H, and the number of healthy and susceptible people at time n plus 1 in the next time step would be, and the way that I'll calculate it is based on the original total population, capital P, minus the number of people that have become infected in that time step, minus the number of people that have been cured in that time step, and subtract the number of people that have died in that time step. Now, each of these is actually calculated based on the number of people in the previous step. When we look at the number of susceptible and healthy people in time step n plus 1, it's based on the current number of people that are infected and the current number of people that are cured and the current number of people that have died, subtracted from my original population. But really, of course, each of these values, the infected, cured, and died at time n plus 1, are all, of course, based on what those infected and cured and died populations were in the previous step, as we have just determined in these lines above. And so I'm just pointing out how, of course, the number of people that are susceptible at time n plus 1 is based on the number of people that were susceptible and infected in the previous time step, and based on the number of people that were cured and the number of people that had died in the previous time step. So the future number of healthy and susceptible is based on the previous populations of all of those different categories. This value, number of infected at time n plus 1, is replaced right here. And this value, the number of cured at time n plus 1, is just this expression here. And the number of people that had died at time n plus 1 is just this expression here based on the number of people that had died in the previous step and the number of people that were infected in the previous step. So this is now an implementation of those formulas and algorithms that I just derived in Excel. And you can see in the top corner that I have first the number of contacts that a person could encounter, the number of contacts they make on average each day. So I'm counting off day 1, day 2, day 3, and that would be the number of contacts on average each person makes with other people in the population completely at random. Right, so whether they have the infection or not, they still go about interacting with other people. And in this case, let's say an average of 10 interactions each day. I have the probability of actually transmitting the disease from an infected to a susceptible person at just 10% here, and the cure or recover rate is 5% or 0.05, and what that really represents is basically 5% of the people that are infected each day are recovering, and then they remain recovered and they won't get the disease again. And then there's a death rate here representing, essentially it means that 0.1%, this 0.001 is 0.1% of the people that are infected are dying each day. I have an initial number that's infected of 100, and I have an initial total population of 1,000 here. And this is kind of a worst case scenario. You can see that it just shoots right up to, looks like pretty nearly 900 almost 90% of the population before it falls back down. Now, why does it fall back down? It falls back down in the number of people infected, first because some people are recovering, and as you have more and more people that are infected, there are less and less people that are susceptible in this population because the population is fixed at 1,000 people. So as more people become infected, there are less people to infect. And so the total number of people that are infected eventually starts to go back down. I'll just interject here with the obvious point that the number of infections decreases after its peak because the probability of encountering a healthy, susceptible person is reduced because there are fewer healthy, susceptible people as more people are infected or cured or die from the disease. In this particular implementation, like with these values, it's like 85% of the population is infected in like 6 days. So that's really terrible situation. So one of the first things you can do is reduce the total number of contacts. Let's cut that down to 5 contacts, and you can see a little bit of an improvement there. Still shooting way up. So by reducing the number of contacts, and that's the idea of the physical distancing, of course, if I cut that down to just 3, then I'm cutting down the total number of people that each person encounters on a daily basis on average, and so reducing the chance for transmission of the disease. And then, of course, another thing that you could do is reduce the probability of transmitting the disease. And of course, that's the idea of wearing face masks and washing hands and so forth. So if I was to cut down that probability 0.05, let's say, that's also bringing down the total number that's infected. The peak is pushing it out later, and it's actually lowering it as well. Because what's happening is that we have these people that are infected still going about the population, interacting, but with fewer people and with a lower probability of transmitting the disease. And so it just never reaches as high a number. And as the number of people infected increases, the number of people that are susceptible is actually going down. And so there's less susceptible people to encounter. And also, of course, as the number of people that are infected continues to grow, the number of people that are cured continues to grow. And as the number of people that are cured and no longer susceptible increases, that drops the number of people that are infected. Okay, and so another parameter that I can adjust here would be the cure rate. And I said that there was no accounting for a vaccine in this particular model, but you could sort of imagine the effect of a vaccine is increasing the recovery rate. So more people are recovering quicker. And that's one effect that the vaccine could have that you could sort of include in this basic model. So if I increase that to 0.1, that is each day 10% of the people that were infected on average were recovering, that's another thing that can dramatically reduce the total number of infections. And the result looks like that in this model. So maybe one other thing that I'll point out just about the implementation here in Excel. I think it's so. First of all, I've got these initial total number of infected people and initial population that I can adjust. We can make that start off with 500 and make this maybe, let's say, 10,000, and the calculations are all following in the same way as before, but I think that it's difficult to read even just in Excel normally, but maybe even more so in a video. So maybe I won't spend too long talking through the implementation, but you can see that what I'm doing here is I'm taking the amount that's in cell B6, which is the total population, and subtracting the values that have already been determined for the number infected. So this just gets copied right down, the number of initial infected people and the number of cured and those that have died. I'll set at 0 initially in this first row. And then what's happening, really, the way that the Excel calculation is being done is that I'm just calculating the number of new infected people at each step, using exactly the formula that I had described before, using the previous number of infected. I'm multiplying by this cell B1, that is the number of contacts, this B11 over B11 C11D, that's the probability of encountering a healthy susceptible person. We multiply that by cell B2, which is the probability of the infection, and then we multiply that by the number of currently infected. That's that C1 that's out, C11 that's out here outside the parentheses. You could put it back into every single one of these factors, but it's just written out there at the end. One of the things that's kind of missing in the implementation in Excel here is that what's happening, of course, is the number of people that are infected is growing exponentially, and it's possible that you can create enough contacts that and a high enough infection rate that you're generating more new infections than there are remaining people that are susceptible. And so the Excel file breaks in that situation. So these numbers can't be too high. Otherwise, this just doesn't account for that possibility that you just basically increased in number of infections even higher than the remaining number of susceptible people. It just would sort of hit the total number right there in the next step. The number of new infected people would actually be greater than the number of remaining healthy people. And so this isn't working if these numbers are too big. This is a simulation on the website prajwalsouza.github.io that was inspired by another video on modeling the pandemic by 3 Blue 1 Brown on YouTube. I recommend checking out this website and that video by 3 Blue 1 Brown if you find this topic interesting. I'm showing this here because I think this is a nice visualization of what's being modeled in my calculations. The parameters for the simulation here don't exactly match what I'm doing in my calculations, but this is close. I think the infection radius referred to here is similar to the value I'm using for probability of an encounter in my calculations, and there's a chance of infection here similar to what I'm using. And overall, the simulation produces a result very much like the result of my calculations in Excel. It's just a nice way to visualize the calculation that I've done. Here, we're starting around 10% of the population infected and reaching a peak of around 40% of the population infected before the number of infected people begins to drop again. In this animation, remove would refer to just those that are no longer susceptible. Either they are cured or they've died and they are removed from the category of healthy and susceptible people. Okay, so what I'll do now is make a comparison between the discrete time model that I just developed and demonstrated in Excel and this classic SIR model that is a subject that is really from the differential equations class. It's a calculus-based model. It's a very simple model for a pandemic. And I think it's, the purpose here is kind of like understanding one model helps to understand the other. So if you followed the previous, it might help to understand this. And if you understood this, it might help to understand the previous one. And just making the connections between the two, I think is interesting mathematically. So that's what I'll work on in this next part of the video. So if you aren't familiar with the SIR model, a quick recap of what it is. Of course, we have the three categories, the susceptible and healthy, that's S. I represents the number of people that are infected in the population. This capital R represents the total number of people in the population that are recovered or removed. Removed in the sense that they can no longer get the disease. They are not infected and they are not susceptible any longer. So just like the discrete model that I just developed, there's an assumption here, a very simplifying assumption, that once you've contracted the disease, you can't get it again. So that is a simplifying assumption in the model. I think it helps remind me to make this comment about how there's like no model is perfect and no model is exactly matching real life, but they are still useful in studying and predicting and understanding real life. So what we see in these three equations on the left-hand side here are derivatives. They are the rates at which each population changes over time instantaneously. That's why we use these differentials. dt, ds dt is the rate of change in the population over time. So for example, the change in the susceptible population over time, the rate at which it's changing is proportional to the number of people that are susceptible and the number of people that are infected. So if you had lots of people that were susceptible and lots of people that were infected, you would have a high rate of increase in the number of infected people. But is this expression, this equation expresses the rate at which the susceptible population changes, is it would be negative. It would always be negative so long as you had both susceptible and infected people in the population. If either of those went to zero, you would have no longer any change. And as long as you had this positive growth rate, as long as that wasn't zero, then you would have a decrease in your susceptible population. And the rate at which the susceptible population changes is given by this expression. So the drop in the susceptible population over time is proportional to the size of the susceptible and infected populations with this constant proportionality R, that is the growth rate of the disease, and it's negative. Now, the rate at which the susceptible population is dropping is included in the rate at which the infected population would be increasing or changing. So whatever I'm losing from my susceptible population, I am adding into the infected population. That's the rate at which the infected population is changing. But of course, the infected population, that rate at which it's changing, is affected by the rate at which we have people being removed. So the rate at which the removed population is changing is based on the number of people that are infected. So with the rate at which that removed population changes over time is proportional to the number of people that are infected. And the additions to the removed category are exactly what's being subtracted in the infected category. So what I'll do here is, just to make the connection with the discrete model that I've already introduced, is we could just multiply both sides of these equations by this differential amount of time. So these are now, in the calculus model, they're infinitesimal, instantaneous increments of time, but just imagine that they were small amounts of time, and then I could multiply both sides by that dt and write it this way. So you can see that I can imagine this change in the susceptible population, change in the infected population, change in the removed population as just being some factor times some increment in time, each of these some factor times increments in time. And then imagine that that increment of time, that differential amount of time, was just one unit of time, whatever time units we decide to use. Like a typical thing, we could just refer to each increment of time as a day, but it could be smaller increments of time or bigger. That's an arbitrary decision in building the model. So imagine the dt was just units of time, and so that would just disappear in the expression as I'm writing it here if the dt was actually a discrete increment of time that was equal to 1. And then we could just say changes in the susceptible population are proportional to the number of interactions. And now we just have these individual expressions for differential amounts of change in each of the populations. Change in the susceptible population, change in the infected population, some incremental change in the removed population. So then let's take a look back. That was actually the discrete model that I developed, right? I've already gone through that. And by the way, calculus is actually easy once you get past all the algebra. It looks easier, right? This expression in the calculus model is actually a simpler expression. One of the appeals of calculus is right there. So that looks much more complicated. But what I want to do right here is make the connection with this back to the expressions in the standard SIR model. So the first thing that we could do is just recognize that the I sub n plus 1 is this future number of infected. I sub n is the previous or current number of infected. This is the next step number of cured based on the previous number of cured, and the next increment in time, the number that it died is based on the current number that it died. And I'll just move all of these current I sub n, c sub n, d sub n over to the other side of the equation. So I'm just going to subtract them over to the other side. So I get these differential amounts of the populations. So that right there is just moving each of these terms over to the other side of the equation. And I will deal with this equation in a moment. So that each one of these then becomes some differential in the number of infected, the differential in the number of cured, and the differential in the number that had died. So let's just focus on those for a minute. I'll take that number of healthy susceptible, that change, and develop how that works out in a moment. So I'm just put that off to the side and I'll come back to it. So I'm focused really on just the change in the number of infected, the change in the number that are cured, and the change in the number that have died. And those, the change in the number of infected, I'll just say is a delta I, the change in the number of cured, that's some delta C, the change in the number that have died, that's some delta D that represents the change in that population. So that is basically the SIR model really starting to come into focus. However, in this particular model, the way that I developed it, the discrete model, I had a cured and died separate. So what I could do here is just recognize that the number that are removed is just the sum of those two. So we could just factor out this negative here and put this C plus D coefficient together as one single coefficient, and just refer to that now as the change in the removed population. It's proportional to the number that were previously infected. Oh, that's one other thing that I've made a little change here. I'm going to move this probability of an infection times the number of contacts. I'm going to move that into the numerator and slide this factor over there so that I can recognize that this is essentially the R, the lowercase r, the growth rate from the SIR model. So then it's really this that I'll now just say that C plus D is some A value, and this is something that I can recognize is essentially equivalent, although not exactly the same, because in the SIR model we take that lowercase r to be a constant. And here this isn't really a constant because the total size of the population the total number of people that haven't died is changing. These values in the denominator change even if we held those numbers in the top constant. So there you can really see pretty clearly how I'm beginning to relate these two different models, the discrete model and the continuous SIR model. But the one piece still to connect is the change in the susceptible population. In the SIR model, that is this population S. As I developed it in my discrete model, I called it H. That was the healthy and susceptible people. Let's take a look at that. Still need to show the healthy susceptible changes are the same in both of these models, or essentially the same. They're actually technically not exactly the same. In the SIR, in the standard one, we take a constant for the little r, and over here it won't be exactly constant. So now this was the calculation for the number of susceptible people at time n+1. It's based on actually taking the total original population in the model the way I developed it, and subtracting the number that were infected at that time step and the number that are cured at that time step and the number of died at that time step. And you remember the way that I developed it was I was calculating the number that were the new number infected at each step and then subtracting it from the original population. Okay. So the way that I was getting the new number of infected was pretty complicated, right? It was the current number infected, and then I had this factor that I was multiplying. It was basically proportional to the number that were healthy and infected. And it was that the probability of transmitting the disease and the total number of contacts and the probability of encountering somebody that was susceptible, and then multiply that by the number of people that are infected in the population. And then I'm subtracting the number of people that were that were cured. It's some cure rate times the current number infected, and then subtracting the number of people that had died at the previous time step. And that was some fraction of the number of people that were infected. And all of that in yellow here was the number of people infected at the next time step. Similarly, I'd calculate the number of people cured at the next time step based on how many were cured, plus that cure rate times the number infected, and calculate the number of people that had died, will have died in the next time step based on the number that had already died times some rate that they're dying as a constant rate of the number of people infected. So this was an expression for the number of people that were healthy and susceptible in the next time step based on all of my current populations in each of those categories. So what I'll do now is distribute this negative out here in front of this whole entire expression. So that makes it a negative I sub n, negative p times n. Take this negative and multiply here, get a plus. Take this negative here, multiply, get a plus. Distribute this negative through. Both of those terms become negative. Distribute that negative through, and both of these terms become negative, because now I realize, I can cancel this c times I sub n, and this term here can cancel. This term here can cancel with that term. So simplifying a little bit by canceling this term, and this term, and this term, and this term, I now have this expression here, which is the number of people that will be healthy and susceptible at the next time step based on each of these terms. Now, what I'm really looking for is the current number of people that are susceptible so that I can take a difference and get that differential change in the healthy susceptible population. So what I'll do is I'll just move this p and minus I sub n over to the end of the expression. So first I just moved this term, which has a negative coefficient in front, moved it there, and then I'll just move that p over one more step, moving that constant value p and putting it there rewrites it this way, and there now I've recognized this right here was the total population that was healthy and susceptible in the previous time step, so I can just rename that h sub n. So that's what I've done there, and now I'll move that h sub n over to the other side of the equation and make it negative. So that's it. Now I see my difference in the healthy susceptible population. So I'll call that delta H, and now I see that that delta H is just proportional to the size of the healthy population and the infected population, with these other values affecting the proportionality of that. So what I could do just to connect the two models is I'll just bring this H sub n out to the side here and put this in the numerator. So it looks like that. So this is a constant. This is the probability of disease when you've got the probability of transmission of the disease when you've got an interaction between healthy and susceptible. This was the total number of contacts that began. This is the size of the population that's still interacting randomly, everybody interacting randomly with each other within the population. And so that's close to a constant. And actually, in the SIR model, this is taken to be a constant value. So in some ways, the discrete model has a little bit more accuracy, perhaps, because it allows for a change in this constant of proportionality. It isn't constant anymore. It will change as our population that's still interacting with each other changes. So there I've taken the expression that I just got for the change in the healthy susceptible population and recognized that this is similar to a constant R from the SIR model, and I've got that same expression from the change in the infected population as I had just developed it previously. That is just a positive of that value. That's that R that I just named here. And so it's essentially very similar, almost identical to what we have in the SIR model, as I've written it, sort of taken from the calculus derivatives and just written it with differentials in each of these populations times some unit increment in time. And yeah, the change in the removed population is a combination of the number that have been cured and died in my discrete model, and that matches exactly with what the SIR model does. And I could just take my R value. It wouldn't be constant in the discrete model, but I could just take some initial value there and use that and compare the two models. And so maybe that's the next thing to do here. So for an example, with some specific values to compare the results in both of these two models, let's take the product P times N to be 0.2. So it doesn't really matter what the P and N would be separately as long as together their value is 0.2. For example, you could have a probability of 20% of transmitting the disease and an average of 1 contact per day, or you could have 10 contacts per day and the probability of transmitting the disease is 0.02, and together those make 0.2. So we'll take that as a given value to start. Let's take the total population to be 1,000 and the initial number of infected people to be 100, a cure rate of 0.05, and let's make the death rate 0 so that being cured is the way in which people are removed from the population. So in finding the R that I would use, the little r that I would use in the SIR model, it would just be that P N over the total population now, because being cured is the way in which people are removed from the susceptible and infected groups. So let's say that we would have initially 900 people that are healthy and 100 people that are infected, and let's say initially nobody cured. So this P times N, that's the 0.2, and 0.2 divided by 1,000, that gives me 0.0002. That would be my growth rate, little r, in the SIR model, and the A, the rate at which the infected are removed, is this combination of the cure rate and the death rate, which I'll just say is 0.05 from the discrete model. Now, putting those values into the discrete model in Excel, I'll just take the capital N to be 1 and the little p probability to be 0.2, so that the product of those is 0.2. I've got the cure rate set at 0.05, and I'll put the death rate at 0. I'll have an initial infected population of 100 and a initial or total population of 1,000 to begin with. So I'm beginning with 10% of the population infected, 900 susceptible, and let the Excel file sort of solve this set of differential equations ultimately, right? And it looks like it's going to peak around 43% of the population infected around day 24. And now let's put those same values into the SIR model and solve that. Now to solve the differential equations for the SIR model, I'll use this GeoGebra app, which is basically solving the set of simultaneous nonlinear differential equations, which would be really difficult to do by hand. In fact, what this is really sort of highlighting here is that the way that you would solve these is essentially numerically, which is essentially what the Excel file is doing. And so really it's all coming down to churning out the values of each of these functions over time. And here what I've done is I've manipulated this. Typically we would set this like total population to be 1 for 100% of the population, but I've adjusted it here so that it matches more closely with the discrete model in Excel. And so I set the initial population to be 1,000, my initial number of infected to be 100, and therefore I have initially 900 people that are susceptible, and I have 0 removed initially. I set the transmission rate, which is that little r in the SIR model. That's the 0.0002 that I calculated already for the discrete model, from the discrete model, and there's the recovery rate, 0.05. I've adjusted the time scale here to about 200 days, and of course I'm getting pretty much the same result that I got in Excel, where it's peaking at around 43% of the population just after day 20. In fact, there's plotting the point 22, 430, roughly 430 is roughly 43% of the population, is right about where we see the maximum. This is a really great a story for another video about finding that maximum point using some pretty fancy calculus. Definitely going to have to save this for another video. But yeah, that's it. That's demonstrating that the two models are really doing the same thing. Now, looking back again carefully at the Excel file and the discrete model, the maximum here was about 441 infected, or about 44% of the population, and on day 22. And the reason for this slight difference in the two models is due to the discrete model computing new totals at individual one-day increments, whereas the SIR model, assuming continuous functions for these values, breaks up time into much smaller time steps. Of course, since the SIR model is solved numerically and on a computer, ultimately even the continuous functions in the SIR model are analyzed with a discrete model. So, okay, I love calculus, but I think that's a point for team discrete. Okay, so now to move to the last point that I wanted to explore in this video. At the start of the video, I developed a discrete model for a pandemic and implemented that model in Excel, and I've now compared that model with the SIR model. But I'm also interested in comparing that discrete model with another discrete model, which is the Markov model. So the fact is, a full comparison with the Markov model really requires a whole entire video devoted just to that purpose. There's a lot to delve into there. So I'm going to mention a few thoughts, and perhaps I can come back to this in another video later. First of all, a fundamental to the standard Markov model is the idea of the transition matrix, and the standard Markov model requires positive entries in the standard transition matrix, representing probabilities that elements in one category would move to another category. And further, a Markov model uses matrix multiplication of the transition matrix with the initial state vector to produce the next state vector. When I defined the rules for computing new totals in each category in the discrete model that we developed here, I'm not simply multiplying probabilities with a current state vector. For example, the new number of infected people at time n+1 in the discrete model involves a probability, but also the product of the previous number of infected and susceptible people in the population. And the number of healthy, susceptible people at the next time step is not based simply on a probability, but it's computed from taking the original total population and subtracting those that are infected, cured, or had died. Some other interesting differences with the discrete model that was developed here and the Markov model is the way in which the Markov model transition matrix would provide direct insight through the eigenvalues and eigenvectors of the matrix into the ratios of the values of the state vector, the steady state vector, that is, or the long-term behavior of the population. That's not possible with the discrete model that I developed here. I am able to compute, or at least estimate, the maximum number of infected in the discrete model, and I was using a formula derived for the SIR model to find that maximum number of infected. But I am not able to determine at the outset what the final totals are in the discrete and SIR model without running through the full calculation of the populations or just numerically solving the equations like I did in GeoGebra. So that brings me to a last point. I've shown the discrete model I've developed here is actually essentially the SIR model, and thus finding the long-term behavior of the population in either amounts to solving and running the simulation, either by computing all the rows representing each day in the discrete model or solving the system of differential equations numerically, like in GeoGebra. This suggests another mathematically interesting point. With the recursive nonlinear nature of both the SIR model and the discrete model that I developed here, we do see a sensitive dependence on the initial conditions, whereas in the standard Markov model, by computing eigenvalues and eigenvectors of that transition matrix, I do have direct insight into the long-term behavior of the system. Okay, so that's it for now. I'll stop here. And again, to sum up, I have developed in this video a discrete model for a pandemic and implemented it in Excel. And I've compared that model with the SIR model from calculus and differential equations. And now I've reflected some on the difference between that model and the Markov model from the video that I'd done before. And I'll just have to put off a further exploration into Markov matrices and determining the long-term behavior through computing eigenvalues and eigenvectors, something that I put off when I did that previous video and I'm putting off again, but I would like to come back definitely in the linear algebra course, but perhaps also in another video here. So thank you very much for watching. I hope this has been interesting and educational, and thank you again.